Hi, my name is Jeff Hammond. I'm a principal engineer at Intel, and I'm going to be talking about oneAPI. In particular, I'm going to be talking about how we are using GitHub to build oneAPI, as well as how oneAPI users are integrating with many of the features of GitHub to consume it in their own projects. The outline of this talk is going to be, I'll introduce myself just so you know where I'm coming from. I'll explain what oneAPI is. I'm going to talk about something called Dpc Plus, which is one of the important components of oneAPI that I use a lot and like. And I'm going to talk about how Dpc Plus is an open standard portable programming environment and show you some demos on both Intel hardware and other hardware. I'm going to talk about how we're using GitHub to build oneAPI, and that includes both the source code and the specification and documentation. And then finally, I'm going to show you how oneAPI integrates with workflows, both the Intel workflows with GitHub Actions, but also some of our downstream user workflows that are taking advantage of the fact that oneAPI is open source and on GitHub and otherwise available to them freely, and then how they integrate that into their open source projects that are, of course, hosted on GitHub. So this is me on the left if you want to know how I appear on GitHub, and you can look up my username if you care about what I use GitHub for. Just for context, so I'm not a professional computer scientist by training. I have a PhD in chemistry, and I've been educated in the School of Hard Knocks, primarily at United States Department of Energy National Laboratories, first at Pacific Northwest National Lab, where I started building software when I was about 25, halfway through grad school, so it's never too late to start if you haven't started coding yet. And I then moved to a place called Argonne, which is outside of Chicago, and I started using GitHub quite heavily there, and in particular to build software for supercomputers. I've been at Intel now for about 6 years, and I work on a bunch of different projects in hardware and software, mostly related to high-performance computing. oneAPI is an industry initiative to build a portable, open standard programming environment for a wide range of hardware architectures, as well as a wide range of application use cases in high-performance computing, AI, data analytics, and other workloads. On the hardware side, it's important that oneAPI supports Intel's hardware, which already include Intel CPUs and GPUs and FPGAs and other accelerators, but also those from other vendors, which is why we've made something that's an open standard with open source that other vendors can come in and contribute to, both the definition of the language and the libraries, but also do implementations for their architectures without having to start from scratch. oneAPI is designed to support a wide range of application use cases, including those where a direct programming model is required. And for that, we have Data Parallel C++, which is based on modern C++, but includes a number of features that are designed to support heterogeneous accelerators in an efficient way. We also recognize that not everyone wants to write direct programming, and that APIs are an incredibly useful part of the machine learning and data analytics ecosystem. And so we're supporting things for deep learning and other data analytics algorithms in optimized libraries that are also part of the standard environment. And we're exposing those things in both C++ and things like Python. So Data Parallel C++ is a part of oneAPI that I work on the most, and Dpc++ builds on modern C++, so those are the features, from C++ 11, 14, and 17, as well as what comes in the future, and adds to that features from ChronoSickle, which is something you can find out about more on the ChronoSickle website. And then finally, we had Dpc++ extensions, although this is a bit of a moving target because what we created as the original set of Dpc++ extensions have now been ratified or are about to be ratified in the Sickle 2020 provisional specification, which means that we started out as something that was open in the oneAPI ecosystem, but then we worked with the community to make it part of Khronos, and of course we will collaborate long-term with the ISO community. So the goal is that all of this stuff is open standard and that it flows from where we start with it to the most standard, most widely available part of the C++ programming environment ecosystem. One of my favorite parts of Dpc++ is that it's hosted on GitHub. It's built based off of the Upstream open source LLVM project, and we are rebasing on a regular basis, so it's consistent with what you'd experience in a recent version of Clang and LLVM. And we're building these extensions in the open, collaborating with anybody who wants to contribute and build on LLVM, which is of course a world-class compiler framework. And what we do with our product is just to take what is open source and then productize that and package it up in a way that people like. But you can grab the compiler straight off of GitHub and use that, and I use that on a regular basis. You can build it and you can contribute to it, and I've contributed to porting it to ARM, for example, because I wanted to run it on my Raspberry Pi. So it really is open, it really is portable, and we have a number of people working together on it. As much as I'd like to teach you all about SYCL and data parallels C++ in this video, there just isn't time. Fortunately, I've already created a very basic introductory tutorial, which of course is hosted on GitHub, and you can see on the screen just an example. You can clone it, you can build it for a bunch of different environments, whether it's Dpc++, the product, or Intel SYCL, which is the open source. It's just different program names. You can see how it builds. You can see it's a very simple code, and it basically adds two vectors together. You can find out all about this. Both the source code is on my GitHub, and also I wrote a blog post, which my blog is hosted on GitHub, and that blog post tells you how to install everything from the ground up on, in my case, it was a Tiger Lake laptop that I just bought. I installed Ubuntu, and I installed all the oneAPI stuff using apt, and then I built all this. So you can reproduce this yourself, and you can take as much time as you like to learn about Dpc++. Now I'm going to show you just a little bit more about how Dpc++ is a portable environment to a variety of hardware, starting with Intel CPUs and GPUs, which I show on the screen. This is another project. It's one of my favorite GitHub projects that I work on quite a bit, and it just shows how you can run Dpc++ code on CPUs and GPUs. This is the exact same code compiled for two different devices. I've also done something similar on FPGAs, and I've done the same thing on other vendors' architectures, including NVIDIA GPUs and ARM CPUs. So this is really widely portable, and I'm going to show you some examples of that in the coming slides. The important thing here is not the performance. This is just a demo. You can grab the code and test it out locally, but you can grab all this stuff off GitHub and see how it goes for you on your hardware. One of the great things that happened for oneAPI and Dpc++ in February was that our friends at CodePlay contributed support for NVIDIA GPUs, which took the idea of an open standard portable environment from an idea to something which was practical and real. And of course, the best part about this is it all happened on GitHub in the open for everybody to see. Everybody could analyze the code and talk to each other. And we've, of course, been collaborating for many months now. There have been dozens, if not hundreds, of follow-up commits to improve the quality of this backend, collaborating between Intel, CodePlay, and other folks, including scientists who wanted to use features and helped contribute to the compiler to make things better, all collaborating on GitHub. Of course, just because you find something on GitHub doesn't mean it's going to work the way you think it does. So here I'm going to show how things actually work with Dpc++ with the CUDA backend. I logged on to an Argonne National Laboratory supercomputer called Theta and the GPU partition, which has a DGX A100 box attached to it. There are going to be some details you can find online. But the hardware details are less important here as much as just the software user experience, and you can see some of the details in the screenshots on the next 3 slides. Here's yet another demo of oneAPI components that I've got on my GitHub, which you can check out and read the source code and see how it all works on your own. I'm not going to do it live because it takes a relatively long time to build LLVM from source, but you can see here there's a script in the repo that will do exactly that for you. In the way that's appropriate for this demo. You can see then that I compile for the SYCL CUDA toolchain. You see all the details here. It's a makefile. And then you can see here the execution on CUDA, to which I'll compare SYCL in just a second. Now here we see the equivalent code written in SYCL compiled with the Dpc++ compiler and the CUDA backend running at a similar performance. Again, as I've noted before, this really isn't a performance demo. The performance is close enough for the type of work we're doing. You'll notice that my SYCL code is a little bit faster than my CUDA code. Part of that's because I have a little bit more practice writing SYCL than CUDA. I don't claim that this is perfect representation. This is not a performance tuning demo. But again, you can check all the code out on GitHub and decide what you think about the quality of the code and the relationship to the performance. All right, hopefully I've showed you a bit of how Dpc++ might work for you and how it runs on multiple hardware platforms. But we recognize that in oneAPI, the direct programming isn't the only thing that matters. And so we're going to show now the library components. You can see them all on the screen with their name. All of this stuff is available documentation and links to everything else on oneapi.com. And in the next couple slides, I'm going to show you how we're using GitHub to build all this stuff. So the first thing you can see here is the specification of the different library components, and we're of course building this on GitHub because you can see the edit in GitHub button right there for people who want to modify the website. You can go to the GitHub source code for everything here. In addition to the specification, the source code for the implementation or the interface implementation for all of these components is on GitHub, and you can see where it is right here at oneAPI-source. So we've got a whole bunch of repos here. The most popular ones are highlighted, and these are the projects. So if you were interested in contributing to these or reading up on the source code, hop on GitHub and see how it all connects together. Once again, our friends from CodePlay actually helped us out, demonstrating that this is portable to NVIDIA in practice and not just in theory, showing here the press release from CodePlay announcing that they support the MKL component of oneAPI with a backend based on the NVIDIA BLAS library. As with Dpc++, the collaborative magic all happened on GitHub, and you can see here the first contribution to the oneMKL project for the cuBLAS backend, and there are of course follow-ups to that and additional contributions for other things. And if you want to become a contributor, you can do it on GitHub and interact with all the people who are working on this project. One of the things that we're able to do with Dpc++ and GitHub hosting is take advantage of GitHub Actions to implement a number of the standard practices for developing high-quality software. So this is from Alexei Bader and on behalf of the rest of the Dpc++ team that actually built this stuff. They implement a number of actions, including a pre-merge check for clank formatting, which is obviously important if we're going to work with the LVM community. We need to comply with their style guide. We also do an automatic validation of Doxygen of the documentation, and then do an update to the GitHub Pages host site of that documentation. And then there's also a post-merge checker that goes in and validates a number of the different build configurations and makes sure that both the release and the debug builds work the way they're supposed to. Now, because we're running on the GitHub hardware, we're not able to test all of the hardware that we care about, so we also integrate with Jenkins to do our own Intel QA on some of the hardware that matters to us. Although, of course, certainly I would hope that someday GitHub supports all the interesting accelerator hardware that we're building, and then maybe we can do all of this in GitHub Actions. One of the neat things about GitHub Actions and oneAPI components is it's not just for us, it's also for you as a user. If you're using these components, you might want to see how this stuff integrates. And so my colleague Robert Cohn and team have built a number of templates showing how you can integrate oneAPI components into your workflow. We have some customers using this already, and I'll show that on the next slide. But as you can see here, we're integrating with a bunch of different services that a lot of people are using out there in the open source community. And hopefully these examples get you started and allow you to integrate with oneAPI as quickly as possible. As an example of someone who's found a way to incorporate oneAPI and GitHub Actions into their workflow to make their project more effective is a computational physicist at Lawrence Berkeley National Laboratory named Axel Heubel, who's a friend of mine, and he works on one of the exascale computing projects for the Department of Energy. And as you can see here and find out from GitHub, he's able to use apt, directly integrate with the oneAPI install process on Linux, pull those components in, set them up, use them, and be able to test with CMake and all the things that he's looking to do. He of course tests with other tool chains. This is not exclusive to oneAPI, but this is just one of the things that we get out of the fact that all of this stuff is publicly available, accessible from GitHub, and has good templates. And I know that Robert and Axel have worked together to debug some of these issues to make sure that the user experience of GitHub Actions and oneAPI is a good one. To summarize, oneAPI is an open standard ecosystem for a diverse range of hardware, not just from Intel. Dpc++ is an open portable direct programming solution for a range of architectures, including CPUs, GPUs, and FPGAs and accelerators of other kinds. oneAPI specifications and implementations are hosted on GitHub. We are using GitHub Actions to streamline the Dpc++ development workflow, which has been fantastic for us. At the same time, we're also building the templates so that hopefully you're able to use oneAPI components in your CI workflows. Finally, I know there was a lot of content here and maybe some of the details were missing, so I'm going to write a blog post, again on GitHub, which hopefully fills in all the details, provides all the recipes for how to reproduce this stuff everywhere, and if nothing else, gives you an opportunity to complain at me for any of the mistakes that I've made. Thank you for your time and for participating in the GitHub universe. This is my first time. I love GitHub, and it was a fantastic opportunity to be allowed to speak with you today.